Welcome to today's lecture, System Level Programming. We are talking today about different topics, A3 primarily, so we will look at A3. We will also talk about A4, shared memory. And then, of course, we will start with a small recap quiz. And for that, you have to go to Menti. You find the link up here or down there in the YouTube description. And I will just open the Menti. Okay, so you should be able to log in already. It will ask you for some name, I guess, so that you can participate. Yeah, and here we go to the first question. 6 questions today. We start with one that is a recap from last lecture, or maybe the last 2 lectures. Okay. So there are 46 people already in here. Let me just answer one question before we start with the quiz. Can we talk in A3 about the answers, or would that count as plagiarism? So it depends on which detail, right? Because we scan for similarities in all kinds of aspects in A3, and if you don't have code that proves that you solved it independently, then this can become a problem for you. Okay, let's see. We start the quiz. We have 51 people now in the stream in Menti. So we start the quiz with the first question. And if you answer fast, you get more points. Race conditions. Race conditions means that 50% of the time a wrong result is produced, or race conditions can only lead to corruption of the corresponding variable, or race conditions can lead to completely unpredictable program behavior and crashes. Yes, and most of you got it right. It can lead to basically anything. The others were just decoy answers. It is not restricted to that one variable. Imagine if you have a race condition that corrupts your stack, then something completely unpredictable can happen. Or if you have a race condition 50%, that also, maybe let's ask one more question on this one. 50%. Next question on race conditions. Which is the worst of these race conditions? The error occurs absolutely always. The error occurs 99.99 something % of the runs. The error occurs in 50% of the runs. The error occurs in 0.001% of the runs, or the error occurs absolutely never. That's more difficult already. Yes. Most of you got it right again. If the error always occurs, then probably it's not a race condition, because if it always occurs, then there's no race apparently. The same goes for if the error never occurs. If the error never occurs, then, I mean, what are we talking about then? So then we have, if the error occurs like 99% of the time, so most of the time, no, that would actually be very convenient to debug, because you would find the error very soon. 50% of the time also would be quite convenient to debug. These are the worst, like they occur very, very, very rarely, and it's super annoying to debug them. And in some cases, so when I debug race conditions and I can't get into a situation where I can reliably get the race condition like in almost every run, The first thing that I do is I try to get from this state into this state by modifying the timing of the program, by adding schedules here and there, by adding sleep statements, by changing the timing. I try to move away from this super bad condition to this perfect condition for debugging. Why is it actually called a race condition? Have we covered that, or did we just say race condition and we are happy? So if you would imagine two threads running through the program code, it's sort of a race. In German you would say a Wettrennen or a Wettlauf, a race for who comes first. For instance, who increments the variable first and then who continues into some condition, for instance. So it's a race condition is a situation, where two or more threads race for one resource, for some operation on one resource. Okay, let's continue with the next question. Spinlock versus Mutex. This one is also interesting. Let's see. Spinlock versus Mutex. Spinlocks consume less CPU time than Mutex. Mutex has a higher latency. Mutex is better on multi-core systems, or Mutex is better on single-core systems. Exactly, Mutex has a higher latency. The Spinlocks consumes less CPU time than Mutex. That's not generally true, because it does a busy wait usually, and that's consuming more CPU time usually. The Mutex is better on multi-core systems. Actually, no, I would say the Mutex is better, the Spinlock. If you compare the two, on a single core system, the Mutex, I would say, has advantages, but it's not clearly better. There are some situations where a Spinlock is still better. Is the Mutex better on a multi-core system? On a multi-core system, a Spinlock even gets slightly better than on a single core system, because you have more often a situation that two threads are working on the same resource. So one has it locked, the other wants to lock it. And as they are running truly in parallel on multiple cores, Spinlock can sometimes give you some performance benefit there. There are some comments in the chat also on which are the worst race conditions. So we have here one comment saying the worst is probably so rare that you don't even notice that it is there. And another comment, the worst one is the one that no one ever sees, but it's still there. Yes, so rare that you don't notice it, or so rare that you never see it in a controlled situation, and then it only occurs in production. That would be really bad. Mutex versus condition variables is the next question, question 4 out of 6, and after that we go for the first leaderboard for today, and then I have some questions at the end, I think, but I will check in a second. Mutex for condition and condition variables. Condition variables are used to notify other threads about an event. Mutexes cannot be used without condition variables. Condition variables are better than mutexes, or mutexes are used to protect other threads from an event. Oh, and that was not a lot of time. Yes, and the first answer is obviously correct. They are used to notify other threads about an event. You signal an event to some other threads. Mutexes can be used without condition variables, totally fine. Mutexes are used to protect other threads from an event. Not really, I mean, an event doesn't do anything to them. Yes, let's see, we have the first leaderboard, and Spinlock got the most points here. And on second place, close behind der Echte. So this is really close at the top. And we will see at the end whether there is, let me check. Yeah, no, we can follow up with this question immediately, but now you know that it's pretty close at the top. So let's continue with the fifth question right away. And this one is, you also remember this maybe from the lecture. Is it possible to successfully use array instead of array I in a program? Yes or no? And again, the timing gives you more points if you answer faster. And most of you got it right. Yes, it's basically totally fine to write array instead of array I in a program. Sure, why not? Yeah, I think for the next one, let's see whether this one makes sense. I'm not entirely sure whether this question, because I showed you last time a program where a number was incremented, and the question was basically which numbers it would print. And I think we already talked about that case. Starting a program twice, what will it print if they start counting at 4 and then increment both or something? And I think it was then, oh no, they were starting at 3, sorry about that. I didn't remember the example from last time, but apparently this was referring to the question from last time. Okay, but let's see, maybe this didn't make a difference here. Actually, it did, so things are completely turned around now. Yes, this question was a bit unfortunate. And now Dritti wins. Congratulations. And with that, we are at the end of the questions for today. I will prepare a quiz for next time, and then you will be able to race again for the points. Okay, let's see. We continue with the slides, and for today, so I said that we want to focus on A3. So if we look at the course overview again, we have A0, A1, A2. So people are complaining about that, but I mean, you can take a screenshot from before the last question, right? And then you still would be at full points. I didn't know, so I was not sure whether it was having the correct numbers in there, because I didn't memorize the number correctly from last time. A0, A1, A2. So we have the compiler, we had C there, we had multi-threading, synchronization. These are all topics that we talked about already. Virtual memory, no, only slightly, right? We talked a bit about it, not that much. Processes, inter-process communication. We talked about processes, how to create processes, how to work with processes, how they can interact. Then inter-process communication, we didn't really do that. Sandboxing, also not really. Sandboxing, I'm not sure what this is about. But, oh no, wait again. Think about it. We talked about sandboxing already. So we had our fork example where we forked the process, created a lot of segfaults, and the segfaults then were isolated in this other process. So your process would not be affected by all these segfaults. And this is actually something that server applications do. When you get a request from a user, you will just fork into another process so that if there is a fault, if the script that the user wants to execute does something stupid and crashes, your server application is not affected. So sandboxing, yes, we talked about that. And at the end, 5 and 6 will be about system programming. But before that, we will continue with A3. And there we had this example on the whiteboard, and this example was basically this here. So we had the example that we just had in the quiz, right? Array I, array at offset I. It's not really well readable. Let me try to improve the contrast a bit. Better? Yeah, it's a bit better. Array I. And think about it, what we have here, array I. So if we now rewrite this is the same as dereferencing array plus I. There's times size of something, but we can ignore that for now. And that's the same as I plus array because of the law of commutativity. And then we have I equals array. Totally fine. Okay, and this works because it's just numbers that we move along here. So these are just numbers, and I will again try to get a bit better color out of this because the color is really not that good. So let's see. Should be this one here. Oh, no. Ah, this is better. A lot better now. Okay. Great. So this is easy to read now. I think I was gone for a second. Maybe I'm back now. Yeah, I've seen that as well. So as I was changing the webcam settings, the tool for streaming just crashed. Now it should be back up again. Okay, so there were some questions about, like, can we learn about Meltdown Inspector? We learn about Meltdown Inspector, so we learn about Meltdown, for instance, in side channel security in the masters. Okay, and but not in SAP. Meltdown maybe also in operating systems. There we will talk a bit about Meltdown, but not a lot. Let's just remove that for now. So we talked about this example. I just wanted to put it on the slides one more time. And we continue with the next part of this pointer thing. So we really talked a lot about all these pointers. We had this example with two global variables, and we ran the program, and it worked, although they were working on the same address, if you remember it from the last time. Otherwise, just click one step back in the playlist and check it out again. So in the playlist, in the last lecture, we had a program running it twice, we incremented the variable, and then we realized that if you run the program twice in parallel, they don't really interfere with each other, although we are working on exactly the same pointer. And how is that possible? And we had another example that was a bit weird. Segmentation faults. Segmentation faults We've all done that, right? Accessing an invalid memory location. How is that possible? Aren't pointers indices into this large array called RAM or physical memory? I thought that's true. I even taught the students that this would be true. Let me check whether I can still get you some more space there, or maybe I move myself a bit down because I think I'm occupying too much space on the slides here. Okay. So how can that be possible? How can addresses in physical memory, how can they be invalid? And the answer is that pointers are not addresses or indices in a large array called RAM or physical memory. They are not. But in a large array called virtual memory. And this virtual memory is specific to one process. And there's a big map that translates pointers, virtual addresses, to actual physical addresses. In SLP, or as a user space programmer who never wants to learn anything about operating systems, or maybe not just yet, as a user space programmer, we don't have to care about that. We just know it exists. We don't care how it works, what it does, how it's implemented, how it's configured. We all don't care about that. That's operating system stuff, and we don't want to talk about that here. We want to talk about the parts that matter for us as user space programmers. The thing is, we never see actual physical addresses. We only see virtual addresses, pointers. And because this table here, this mapping table, this large map, the big map to translate pointers to actual physical addresses, this would grow really large, and for that reason it's easier to map it block-wise. So we map a block that we call a page. Different processes can now have the same pointer, the same virtual address, but they will see different things there. And that's exactly what we've seen in the example last time. Okay, let's just check. There are some questions on Menti. How difficult is OS if we do well in SLP? There's a huge amount of variance in that. So I have seen groups in OS that said they had to work 60 hours for the full semester and didn't do anything but OS. And I had students that said, well, it was about 25 to 30 hours per assignment. And that's it, and nothing really, like maybe a few hours on top of that for the for learning for the exam. So it really depends on the individual, on the individual, how much effort it is. So I have answered a question about page size and kernel start code based on my pre-knowledge. Do I need to prove it with programmers where you need to show how you would figure that out? Yes, maybe it's wrong, right? Maybe your pre-knowledge is not 100% correct. You should have some method to verify that it's correct. Warum liegt hier Strom? Okay. Maybe another day. So every process has a virtual address space of 128 kilobytes. That's actually correct. How can we find good teammates for OS? Any hints on that? Maybe ask in the SLP chat. From the scoreboard in SLP how many points the people have approximately. And you can look for people that are approximately in your point range. That's probably a good idea, because then they will have approximately the same knowledge and preparation level that you have. So just maybe ask in the chat and ask someone maybe ask in the chat. Yeah. The cat, maybe later. I don't see the cat around right now. How does the streaming setup look like? I have a very chaotic desk here with a microphone and 2 screens, and here's some whiteboard right next to me that I have a second camera focus on. Does internet research count as a way to prove our answer? For example, if we upload a text file with the link to the website or man page. I would say in general no, because it's quoting someone from the internet is not the same as being able to demonstrate it yourself, to figure out the answer yourself. Do you also teach InfoSec? Yes, I will. In November, I will give some InfoSec lectures. So let's continue. We continue with A3 memory layout and demand paging. So what do we do in A3? We experiment with different kinds of variables, global variables, local variables, variables in shared memory, heap variables, what else? Different specifiers, maybe sometimes with the static variables, then not static, maybe const, all types of different variables, and see what they change in the behavior of a program, or if they change anything. And then we observe how the memory is used in practice. When does it really increase? When does it not increase, although I would have expected that it increases? Or if I type in the question on Stack Overflow, the first result on Stack Overflow tells me this is how it works. And then I try it out and figure out that the first answer that I find on Google is completely wrong. And that's not just the case for one of the answers here in this questionnaire, but for multiple. If you just enter them on Google, you will find wrong answers first. So better try them out. And then answer the questions from the test system questionnaire. You can then register and participate in one of the virtual memory discussions. And this semester we have 2 options here. The one is the same as last semester. We have a virtual discussion, so it's online. And for that reason, we can't have a completely flexible format, but we organize it more like a Kreuzerübung, where you check which answers you are able to explain, and then you will be asked to explain it. Yes, in the chat someone said Stack Overflow thinks that extern is a shared variable in C. Yes, I mean that's really brutally wrong. It's shocking. I mean, if that's the typical knowledge level on Stack Overflow, I would be super careful with taking anything from there. Yes, so in the virtual setting, it's less of a discussion. It's more like a Kreuzerübung where you explain how you got to your answer, maybe demonstrate it, maybe open a screen share and show that on your computer, if you type in this command on the bash command line, then you will see how much memory is used or something like that. How do you proceed? Well, if you ignore this is important. You won't be able to answer all questions in A3. So the steps are: first, answer all questions, question by question. You have to answer all the questions. Then before the deadline, go through them again and undo all answers that you don't feel confident about. If you have to present them, explain your solution in front of the class. So first answer all of them, and then undo all that you don't want to present. Something like I guessed correctly would be not sufficient, and you would get point deductions. Then I read this answer online would also not be sufficient, and you would also get point deductions for that. But or not get any points for that. But it means the same thing. You don't get points for A3 then. We want to have a full explanation for the answer and what we have to do. So what I have to do to observe the behavior that you describe. There are some questions in the chat. When will these discussions be, and will they be held on Discord as well? So for the virtual ones, yes, they will be on Discord, and in small groups. I expect maybe something like around 20 people per group, maybe a bit more depending on how many people we have. And the second question is basically like a math exercise, exactly a Kreuzerübung, like the typical math exercise where you also have to check which answers you have, and here you do the same just by answering them, and then you uncheck them by undoing the answers. What if we do have code and get a solution, but it's wrong, for example? That's fine as long as it's unique to your unique own solution, then it's totally fine. If it's a well worked out answer with code that documents how you got to your result, that will be fine for the discussion part. You won't get all the points because you won't get the points from the questionnaire on that then. But in the discussion itself, a multiplicative factor is determined that is multiplied on the score that you got from the questionnaire. So if you do well, you can compensate on having fewer answers correct in the questionnaire. You will still be able to compensate that. Do we get coins or points for the questions? Points, you get points for A3. There are no coins this time. There's no early submission this time, and no coins, and also no coins in the questionnaire for answering these questions. Don't collaborate with others. We cross-check who did what, when, who answered which question, in which order, how long you have taken to think about an answer, when you have seen a question first, and how long it took you to answer it. And all of these things are just thrown into a big statistics framework, and then we find all the correlations that you never thought of, but the statistics framework finds them anyway. These two people checked out the assignment on the same day, and then they handed it in 2 minutes apart from each other. Interesting. A lot of statistics that you can collect that I don't all want to disclose here. But the most obvious ones is who did what when, like on a granularity of a question. Yeah. Okay. Do we need to tag something? No, there's no need to tag anything except for the code, but the code is only considered in case of suspected plagiarism. We don't look at it by default. Is there an order when answering questions in group of 20, or who first starts to talk? I see what the question is. So the question is how this is ordered. In the offline discussion rounds, this will be more flexible, so you will probably raise your hand and then the tutor will say, yes, please. The other option is the virtual setting, where the tutor will select who starts talking, because they have a list of who answered with which question anyway. So there they will moderate it a bit more in the virtual setting. In the offline setting, you can just raise your hand if you want to say something. With that, we are done with A3, but I will just check out the questions on Menti. Do we have to push any code in A3? We have to avoid cases like where we suspect plagiarism and you have nothing to show how you got to your answers, then this would be very suspicious, right? If you can't show like, okay, I did this is my homework that I worked out, this is how I got to the answers, then yeah. Referring to man pages does not count as an answer. No, you have to demonstrate that you understood it correctly by running a program which does that. So you should run some small program that demonstrates what you suspect is correct. The question in the chat is, can we already start on A4? In Discord, the tutor said it's not done yet. Maybe ask them again today. I think it should be ready because the deadline for A3 is already this week. And I think there should already be a tutorial on A4 on Wednesday. Like a question hour, not a tutorial. Do we have to tag A3 in our repository? If you commit code, so if you want to be on the safe side and commit code to avoid any cases of suspected plagiarism, then you need to tag it, yes. There's also an offline discussion round. Yes, we will highlight which of them are offline, which of them are online, so please be careful when registering. When will the discussion be so there will be about something between 6 to 12 time slots for that throughout the week after the deadline. So that would be next week. Maybe next week or the first week in November, one of the two. Are the questionnaires in English or German? They are in English, but A3, the discussion round, you can answer in German or in English. When we'll be able to register after the deadline, we will send out the first time slots this week, and then you can register, but it's first come, first serve. So as soon as they are full, then we will also announce further time slots. Do we need a webcam for discussion offline? If it's offline, then you just go there and you are there in person with everyone else, together with everyone else. So you don't need to bring a webcam to an in-person discussion. Okay, let's continue with the slides. Shared memory. So we already had this example here, like fork a program like this. You have the process here, maybe the shell, you fork. Then if the PID is 0, then we are the child process, right? The child does not know the parent. It's a cruel word. And then the child will take these arguments here. Oh, it is unfortunately cut off here. Some arguments here. Here it's better. And then it will, for instance, execute bin ls. And now you have the arguments here, so it will call bin ls on the home folder. And so this is what this exec here does in this second process. And then the shell can do further shell stuff. Here we already worked with that. We used wait PID to wait for the child process. And then exec replaces the program. Now your program is running and does something. So think about this second program here. Second program now is in the main function, or in general. What if you have two programs here? Maybe they want to share some information, some memory. So how do they do that? And there are different system calls for that, and we will take a look at them today. First that we want to look at is Shm Open. So we use Shm Open to get a pseudo file descriptor. It works pretty much like a file, but it's not actually on the disk, so it's a lot faster to access. So if you store data in there, it won't go to the disk usually. You have the read-write permission here again, similar as with the OpenSys call. And then the file permissions, if you create a file, then these are the access permissions. Ftruncate, you have to enlarge the shared memory object, because if you just create it, it's 0 size, so you can't store anything in there. With that, I reserve 1000 bytes, so then I can store 1000 bytes in this shared memory object. Okay, let me just check out the questions. The tutor was just saying on the YouTube chat, you can start on A4, it should already be done. And then a second question, when we can't answer a question, we have to submit them anyway. Yes, you have to submit all the questions, and then later on, as soon as you've answered all the questions, go through them again and undo those questions where you feel like, I'm not entirely sure whether my answer is complete enough. If it's wrong, that's fine. If you have a good explanation and it's wrong, that's fine. But if you are answering, if you are saying like you want to skip the question, you don't want to spend any time on it, just click anything and undo it later. Okay, let's see. Questions from Menti. I still have one question here. For A3, yes, you can just create the folder for A3. And then, what do you think about? Do not communicate by sharing memory, instead share memory by communicating. Does it make sense in the C programming language or an SLP context? I'm not sure where this statement is from or what it's referring to. So shared memory is a very simple form of inter-process communication, so that's what we use. Why would I use a shared memory object when it's shared between processes and not threads, right? Exactly, yes. Threads share all the memory. Like you can't really call that shared, because threads run in one address space. There's nothing to not share between them. They run in the same address space. It's like saying like members in one C++ object share the same C++ object. No, it doesn't make any sense to say that. It sounds weird to say that, because they are part of the same C++ object. And it's the same for threads. They don't share all the memory in the process as in a sense of shared memory. They are part of the process. And as part of that process, they can access any memory within that process. It's not shared or not shared. I would not use the word for threads. So shared memory is always between processes. How difficult are A4 to A6 if we had no problems with A1, A3? I think A4 is, if you didn't have any problems with A2, then I think A4 should be fine as well. If you implemented some data structures like a linked list or a skip list or some form of a tree in ESP or SAP, so in Programming 1 or in Object-Oriented Programming 1, then you shouldn't have any problem with A5. And for A6, it's a bit of inline assembly, but also there, it's actually probably so it might be the shortest of the examples with very few lines of code. So I think should be fine. So submit all answers first, then undo them later. We will have points for what we submitted, but we have to explain the remaining after undo, right? You get points for the answers that you submitted. If you undo answers, you don't get the points for them. So you should only undo those answers where you fear you might lose points if you are questioned about them. Will there be a session where we discuss our solutions in the exercise, like how they are right or wrong or how to improve? You can, for all the examples like A1, A2 or A4, A5, A6, you can just write to the tutor and discuss that directly with the tutor. So that is possible. For A3, this is actually the discussion round where you discuss your solutions and whether they are right or wrong, and how to improve your answer finding strategy. We will use x86 assembler for A6. Do we have to uncheck answers before or after A3 deadline? Before. So I'm expecting that you answer all the questions anyway. So there are like 1 or 2 students in the entire course that might not answer all the questions for A3. Almost everyone just answers all the questions, because you have a solution, you document how you found it, and that's it. Then you don't lose any points for that. So that's fine. Can we discuss even after the deadline for A2, like for examples like A1, A2? Sure, just write the tutor, ask them like, where did you lose points? What could you improve? So they would clearly give you some advice on what else you can improve in your program. So let's continue. So we now had this problem here with this shared memory, and I now want to access it. And the problem with this shared memory here, the shared memory object here, and I tried to create. Now I have a file descriptor. Now I don't know how to access it. So what do I do to access this file descriptor? I need to map it. And to map it, we know system calls that we can use for that. So why don't we just take this SHM file or SHM object, the shared memory object, and map it into the virtual memory, because virtual memory is virtual anyway. It's a map, right? It maps to anything. We don't care where it maps. So that is what we do. We use this mmap syscall for that, which we will also learn more about in the future, later in this lecture today. We pass a lot of arguments here, null, 1000. These are read write, map shared. This sounds like shared memory. FD, the file descriptor from up here, 0. Okay, so a lot of things, a lot of parameters that we still need to figure out what they exactly do. Then we fork the process, and now the two processes have shared memory. And that's our starting point for today. We will work with that, and let me just move this one a bit down. Okay, so let's see. I need to switch to the screen share. Okay, that's better. Yes. Okay, let's see. We have the screen share here. We have our SLP folder here, and we had a lot of examples already that we can now work with. So let me just, before I open the files, let me just also arrange things on my side here. So we will start with some rather simple example. I think last time we had this Malloc example where we had gigabytes of memory. So maybe we start with that. So here's our Malloc example. And what we want to do is we want to check out what this mmap syscall does. So let's close this one. Let's open the terminal. And let's make this really large, because I want to check out the man page with mmap. Man mmap. Okay, map. Mmap. Map or unmap files or devices into memory. Okay, let me just make this a bit smaller so that it fits. Yeah, that I don't overlap with it. Okay. I will also move this one a bit over here. Maybe make it a bit smaller. Okay. Great. So let's see, we have our mmap man page here. It says mmap creates a new mapping in the virtual address space. So here it also says virtual address space. I was wondering, is it really necessary that we learn about this? I mean, we are not in operating systems here. And if we're not in operating systems, then why are we learning about this? But if the man pages mention this, then we should know what this term means, even if we are just a user space programmer. So it's good to know that now, virtual address space. of the calling process. Every process has its own virtual address space. The starting address, let me just yeah, now it's better. So the wrapping of the lines looks now nicer. The starting address of the new mapping is specified in address. Okay. So let's see. What does that mean? So we map something in our memory, we don't know yet what. The starting address, so we can specify the pointer where this starts. So we can specify that there at this address, our mapping should be. Okay. The length argument, that's the second argument now. So we have address was the first, length is the second. Length argument specifies the length of the mapping. Okay, that's quite intuitive. I can specify a length for the mapping. That's nice. It has to be greater than 0. Yeah, of course. I mean, it doesn't make sense to map 0 bytes. Then I can't access anything in that area anyway. If address is null, then the kernel chooses the page-aligned address at which to create the mapping. This is the most portable method of creating a new mapping. Okay, so that it sounds like we should provide null here. If address is not null, then the kernel takes it as a hint about where to place the mapping. So what does that mean, a hint? Like, I guess, if I would be the operating system, I might take the hint from the user space programmer and just throw it away. That would be totally fine, right? And that's what many operating systems do. Okay. Where to place the mapping. On Linux, the kernel will pick a nearby page boundary, but always above or equal to the value specified by some address here in some file. And attempt to create the mapping there. If another mapping already exists there, the kernel picks a new address that may or may not depend on the hint. Okay. So it really means that the operating system can do whatever it likes. In this part here, it just says the address might or might not be used, but don't rely on it being used. So better don't use it at all. So the recommended approach is to just provide null. Interesting. The contents of a file mapping as opposed to an anonymous mapping, see map anonymous below, okay, maybe later, are initialized using length bytes starting at offset in the file. Okay, so that's interesting. So we have address now, we have length, and now they're explaining offset. Offset in the file. So that's the starting point in the file referred to by the file descriptor fd. Yeah, we also found that out already, the file descriptor. The offset also must be a multiple of the page size as returned by sysconf page size. This also sounds like something we should use at some point to check what the page size actually is. After mmap has returned, the file descriptor fd can be closed immediately without invalidating the mapping. Oh, that's interesting. So we map a file maybe into memory, and then we can close it, but mmap still keeps it open and can still work with that. So what about the last two arguments? They are still missing, right? Protection prot argument describes the desired memory protection of the mapping and must not be in conflict with the open mode of the file. Okay, so it is either prot none or a bitwise or of one of or more of the following flags: prot exec, executable, read, readable, write, writable, none, nothing. Okay. And then we have flags. We have here the flags argument determines whether updates to the mapping are visible to other processes. So whether it's shared memory. Mapping the same region. Yes, so it determines whether it's shared memory. And whether updates are carried through to the underlying file. Oh, also the file, that also has an effect. This behavior is determined by including exactly one of the following values in flags. Map shared. Share this mapping. Okay, it couldn't be clearer, right? This is shared memory. This is how we get shared memory. Updates to the mapping are visible to other processes mapping the same region. And in the case of file-backed mappings, we can make files, so we can map files into memory. And we can still use map shared to make it shared memory at the same time. So we can have a file that is mapped into the memory and is shared. That's interesting. And they are then, well, if we pass map shared there and you update the data in this mapping, then it's carried through to the underlying file. So that's super interesting. So that means that the file is modified as well if we pass map shared there. So that's interesting. So okay, there's some hint on we can precisely control when updates are carried through, but we might not care. And we have shared validate. I will skip that one. I'm not very much interested in that one. Sounds like a special case of this one. Map private. Here, create a private copy on write mapping. That means it's private. It's not shared. It's private. And if I modify something, I will get my own copy of it, and then it's not shared anymore. Updates to the mapping are not visible to other processes mapping the same file and are not carried through to the underlying file. So this is something that we can use to map a file into our process. But we don't want anyone to see the changes. We use map private. It is unspecified whether changes made to the file after the mmap call are visible in the mapped region. Oh, so maybe we shouldn't do that then. So we shouldn't change the file while it's mapped as map private. There are a lot more flags. We have here something with 32-bit. I don't really know. Here, map anonymous. This was mentioned before. The mapping is not backed by any file. Oh, that's interesting. So it doesn't have to be backed by a file. With map anonymous, we can say we don't care. Its contents are initialized to 0. The file descriptor argument is ignored. However, some implementations require fd to be -1 if map anonymous is specified. And portable applications should ensure this. So if we want to write portable code, we should ensure this. The offset argument should be 0. Of course, I mean, it's not backed by any file. Why would I use the offset argument? The use of map anonymous in conjunction with map shared is supported only on Linux only since kernel 2.4. Okay, I think I have a bit more recent version than that. Okay, but let's go a bit more down. We had we also had the protection flags. They were up here. So let's use this function. It sounds like a good idea to use this function. And if we just close these windows here and check what we had here, we had here the mmap call, and now we will include sysmnh mmap. Okay, anything else? We need to copy these two definitions in there. And now I will allocate memory instead of malloc with mmap. So let's see how that works. So instead of this malloc call, we now allocate this memory with mmap. Mmap null, because it's ignored anyway. The length, well, we wanted to have 1 GB of memory, right? So that's the length. Protection, I don't care. Make it prod read and prod write. Flags, we want it to be map anonymous. File descriptor -1 because it's map anonymous, and offset 0. Okay. Okay. Let's see. So we compile this gcc malloc. Oh, it's not malloc anymore. We should have save this as under a new name, like mmap 1, mmap 1, okay. mmap 1.c. Ah, it seems to work. That's a bit odd, right? That's a lot more memory than last time, is it? We should have 128 terabytes, not this much. Can we just check what is returned here? Maybe we didn't check that if it doesn't work. So let's check that. mmap, what does it return? Where's the return value? So return value. Ah, here, return value. On success, mmap returns a pointer to the mapped area. On error, the value map failed. That is, void pointer -1 is returned. Oh, look at that. Our check here doesn't work. We have to now check whether it's void pointer -1. If it's that, then we're out of memory. Otherwise, I mean, we would be running continuously if we don't check for the correct error value. Let's run this again. Oh, it immediately says out of memory. What? How can that be? Immediately out of memory. Ah, yes, we forgot something, right? mmap. And here it said we need to pass at least one of the following flags: map shared validate, or map private. In addition, 0 or more of the following flags can be ORed. Okay, so we have to specify something here. Let's say it's map private. Just some private memory. I don't want it to be shared. Let's compile this. Let's run this with mmap. Ah, yes, this is working exactly as expected. And interesting. So let me try one more thing here. So I want to try this again with Malloc and compare the addresses here. Yeah, so we have to be careful here. So either it's mmap and then we have to check for null, or this and then it's -1. So this is, yeah, this looks also like similar addresses, right? It starts at very high addresses here, and then it goes all through the address space up to very low addresses. And then if we do the same again with mmap, looks similar. The address now is aligned here, so that is a difference. So we see the last 3 digits are all 0. Interesting. Okay, let's see. And I need to just let some air in because it's getting a bit hot here. Okay. Should be working again. Let's see, what else do we have? We wanted to create shared memory, so let's close this program here and we will continue with our first shared memory example. So let's just reduce the size here a bit of this window and I can see some more. I think the next part that I want to check out is how to interact with files. And what I will do there is I will again create a new, let's call it this mmap files. And this time we will, yeah, maybe we keep this. And what we do is now we create some struct, maybe some config element. Maybe we are writing some program which has a config element pointer. Next, this will be a linked list. And then we store in this configuration of our program, we store basically keys and values. And we have keys that are a string and the values are all numbers. Okay. If we have a linked list, then what we do is we need to initialize this linked list. So what can we do there? So let's think about how I envision how this works. So maybe I have some config that I want to write. So let's think about that. Yeah. So what I will do as a first start, I want to distinguish between two cases: whether I'm the program that wants to read and check the config, or whether I want to create a new config. Okay. I need some arguments here: int argc, character pointer argv, array. Okay, and then otherwise I'm PID1. Okay, so now I have a distinguisher. So I pass either the character 0 to this program or 1, and with that I can distinguish my two programs. Int file descriptor, and then this one opens the game config, and it will open it as read write. And then we want to use some method that we still have to write. It's the method addElementWidth. And this is now, I'm choosing a linked list here as a data structure to also help you with A5. So this is something that you will use in A5. And now for the PID, what else can we do here? So maybe let's start simple like this. Now I have some noise from outside here. Let me close the door again. Okay. Let's see. So what do? We store some data in this storage configuration maybe, and what we do is we at the end want to print what we have there. So let's just print the pointer where this linked list starts. We still have to create that, right? So let's make this here struct config element pointer e, and here we have the cat. Okay, let's see. So config element e, we need to initialize it to 0, but I mean we can do that. It's a global variable. Struct config element pointer e. What else do we need? We need to have a loop where we iterate, or we can first start with this one. Let's just check whether we messed anything up already until this point. mmap files1, and the input is mmap files1.c. Okay, so unused variable fd. Yeah, I guess. addElement. Oh, we don't have addElement. That's a problem. PID not used. So addElement is definitely something we need to add. But let's think about that at a later point. So what we want to do then is we want to iterate over this linked list. And iterating over a linked list, I'm sure that you know how this is done. And there's a semicolon missing element. Current is E, the current element is E, and while the current element is not 0, we continue in this list. And then we always print the pointer, P, the current element, we print the key, which is just a string, right? %s. We print some value that would be this maybe. And we get them from current key and current value. And then we say current is current next. With that, we iterate through a linked list. And at the end, we return 0. So let's see what happens if we run this. It still doesn't like our code here. Oh, read write is not declared. Struct, there's also a semicolon missing somewhere here. Okay. What else are we missing? We have read write open. Oh, we don't have open. So let's check where we get open. Men open. Oh, that sounds like the wrong one. Let's try men3 open. That looks better. So we have these two includes that we need. We didn't include them, right? Yes, we should have checked the men page before. It would have saved us some time. So let's compile that again. So we have, again, the unused variable. We don't care about that. PID is also unused currently, but later it will be used. But it compiled, and if it compiled, we can also run it with mmap files1. No. Mmap files. I have a typo here. Okay. Oh, segfault, a segfault. Nice. Not so nice, right? Why do I get a segfault here? So let's check out what we did. We had our struct config element, and while this is not 0, it will iterate through it, but it's 0, right? Good point for a debugger. Let's try what the debugger says. GDB on mmap files1, run, backtrace. And here you see that I didn't do it correct. I didn't compile with -G for debug. Let's try that again, and we run it. And now we have backtrace. We can see exactly where it crashed in line 23 in the main function. Line 23 in the main function. Ah, yeah, we didn't pass any arguments. Okay. So if argc is greater than 1, then we will execute this code. Otherwise, we don't. Looks good. So now it didn't crash. We probably should have passed 0, right? But it's still doing the same thing. We need to add this function here to add an element to the list. So how does it work? How do we add elements to a linked list? And that's, we will just think about that. And the cat is here a bit difficult to handle right in front of the keyboard. So maybe we can put her somewhere else. Yes. Anywhere else, not just on the keyboard. And then we add this function here, void add element. We want to use a key and assigned size t value. store some element here. And now what we do is we again want to iterate over this list. Config element current is E. And we want to create a new element here. And we'll start with a very simple example here. Config element new element is malloc. How much do we need to allocate here? We need to think about that. I mean, we need space for the key, for the value, and for the next pointer. So what we can do here is we can allocate simply the size of a config element. So this is our new element, and if E equals 0, this is the base case. In the beginning it is 0, and later on it will not be 0. So we have to think about those two cases. If E is 0, the list does not exist yet. Then in that case we will initialize it maybe to our element. But maybe not here. Let's think about that. So this is the case new list. In the other case, we can search for the end of the list, or we can insert it at the beginning of the list. But I will search through the list because I think that's a good idea how to show you again how to iterate through a list. So we search for the end of the list. And how do we do that? While current next is not 0, we haven't reached the end. And then current is current next. Okay, and this should be, of course, this should be a struct pointer. We are talking about pointers here. Also, this is struct pointer. Okay, config element undeclared. Why did I not declare it? Config element looks like it's declared. It should be size of struct. Config element. I really like type defs for that reason, because I don't like to write struct all the time. Okay, so we have new element here. New element is not used yet, but we will use it in a second. So we searched for the end of the list. So in both cases, think about it. Now we have found, so this variable here is now either the new element, the last element in the list, or if there is no list yet, it will still be 0. So in a 0 case, we can just say E equals new element, right? Then we have initialized the list and we're good to go. We probably also should copy things into this element. So we will use string copy for that. So we copy into this new element key, we copy in our key. And that's the first thing. And we initialize also the next pointer to 0. So that's the last, it will be the last element in this list. Okay, so let's see. So we initialize this to 0. If we have found the last element, then we can say the current next should be our new element. And that's it. And this is how we insert elements into a list. Let's compile this. Okay, it says we should include, we should add string.h here. So let's do that. String.h. Okay, got it. It's still empty, but we also didn't add any elements. So let's try to do that. Add element. Yes, it works with value 0. Value 0. What is going on here? Value 0. Ah, yeah, we never set the value. Okay. Here also, this is something that I want to show you. If you take a look at string copy, what does it say here? String copy. Beware of buffer overruns. Oh, that's... See also bugs. If the destination of string copy is not large enough, then anything might happen. Whoa, anything might happen never is a good thing. Wow. This function is similar to str ncopy. String. Oh, this is better. Str ncopy. Let's try str ncopy. Str ncopy. Ah, yeah. Is similar, except that at most n bytes of source are copied. Warning, if there is no null byte among the first bytes of source, the string placed in destination will not be null terminated. Okay, that sounds like the thing we are looking for. String copy, we want to have ncopy. We want to copy at most size of, basically size of new element key, not more than that, and we want to make sure that new element key, the last entry here, let me add a printf here just to make sure that I'm understanding fully correctly what I'm doing. So I will add a printf statement just for a brief second to check whether I understood this correctly. 128. Okay, so this is 128. So 128 is, by the index, we're starting counting at 0. So we have to say size of -1. And we want to set this one to 0 just to make sure the string is null terminated. Otherwise, it could be exploitable. We don't want to make our code exploitable, but we learn more about that in the masters. So this is, you will pick up exactly there. In SSD in the masters. There you will continue exactly here. So the key is initialized. We haven't initialized the value. Let's initialize the value as well. Value. Just see, run this. Yes, width. We can see it here. Width value 1024. Let's see whether this works when we add more elements. So I will add, I don't know, height. Actually, we could use more realistic values there. This one, and then maybe, I don't know, maybe the refresh rate, and it would be 100 or something. Yes, yes, this looks good. Our list is working. Okay, and this is working now with Malloc. Now I want to try something. So so we open this file here, but the file, let me truncate it. So game config truncate to 0. Game config. Okay, now it's empty. If I run this program again, it's still empty because I'm not writing to it. Because if you remember, map private or map private, we are not even using map. We are not using mmap, so that's why it doesn't work. We're using malloc here. We're also not trying to write back to it. So we need to think about that a bit more. So if we want to write this into the file now, this is actually quite tricky because now we have to use the write syscall and so on. That's pretty complex. So maybe we can do something better. Okay. So I want the config to be stored in here, and I will now use mmap to map this config file into memory. And we've seen that there are several steps. First, we don't use open, but Shm Open. Shm Open. Okay, but before we move onto shared memory, you can also show that with regular files. So let's start with regular files. And then we will mmap this one into the memory. We again have 0. We want to map, I don't know, maybe a megabyte. So then prod read, prod write as before, and then flags we have, well, which flags did we have? Let's check again, mmap. What were the flags again? Map shared, map private. Let's try, so we want to write something into the file. So we use map shared this time. The file descriptor, we just have it here, and we want to start at offset 0. That is where we start. So then we need to add elements in there. And this one returns something. So I will set this start of the list to E. That's the start of the list. It starts exactly where our mmap starts. Now we should be able to place the first element there. But now our logic doesn't work anymore, right? Because now it's not 0 anymore, but it's empty. Let's add another element here. And this element is, I don't know, maybe some character which says it's used. And this one then should say it's used. And now we have to be careful when iterating over these data structures. So if E used is 0, then it's a new list. Then we will, oh yes, then we need to change the logic here a bit now. So now new element will be E, right? Because we already have the memory, and we will just fill this in here. We can also remove this, just work right away with E. If the list does not exist yet, then that means that the first element, we can fill that. Okay. Less code, I like that. Okay, and used will now be set to 1. Let's then think about this other case here. While current next is not 0, we can say current is current next. So what do we want to check now? If current next, if current is not used, then actually we are in the same situation again as this one here. Oh, we can make this a lot simpler. Of course. Let's move this part down here. Okay. Current is E. If current is used, is 0, then this is what we do. Yes, that makes a lot of sense. And we now run this on current. It's the same as before, right? We'll just find one nice trick in a second, because we will iterate over the list, and then we need exactly the same code as here. And now I will move this loop up here. While current used is not 0, I will continue and iterate over it. Because for every element that is in the list, it should either be used, or we can use this element right away. And in that case, if the current element is already used, then this can be the case, like current is current next. Okay, let's see whether this works. We don't even have to check this anymore. Code has gotten a lot simpler. The question just now is what happens with this next value, because this one is pointing to 0 initially. Current next now needs to point somewhere else. And I would say it can point to current plus size of struct config element. So why is that the case? So let's think about that. We now allocated some memory, right? We got memory with mmap here. So mmap points here. The result from mmap points here. Now we have our first element, we place it here. We place the second element right after that. And the third element right after that, and so on. So we just place them right one after the other into this memory area. And that's why this makes sense to just add size of struct. We already have the memory, we just need to organize it. Okay, so current plus size of struct. We have a big block of memory now. We can use it in whatever way we like. We run this, let's see. String copy discards volatile point. Yes, I mean, I don't care about that part. So if it's something that I should do, then probably I want to cast it to a character pointer or a const character pointer. I don't know, it was the other one, right? No, string copy discards volatile. No, it's fixed now. Okay, so it's gone. PID is still unused, but I know that it's unused. Bus error 0. Okay, bus error. Why do I get a bus error? I'm trying to write to this shared memory, and the thing that I haven't done yet is ftruncate. Exactly. If you check out the man page of mmap, it says something about ftruncate. Does it? And Shm Open. Shm Open says something about ftruncate. Interesting. So, but why does it not work then? So let's see. We have our mmap here, prod read, prod write, map shared. Let's ask the debugger, GDB. So we need to compile this, of course, with debug flags, then GDB, mmap files 1, run, backtrace in add element. Oh, now we are not. So in add element, it's crashing in line 25. Line 25. Why could line 25 be crashing? Because current in the beginning could be 0. We can use assertions here. How do assertions work? Men assert, like men3 assert. Include assert h. Assertions are great because you can add any expression in there and it will make sure that it's really, really the case. So what I want to make sure here at this point is that current is not null, and also current should not be void pointer -1. We want to compile this again, run this again, a bus error. And where do we have it? In line 28. So apparently line 28 is a problem. So while current used, it's not 0, crashes. So if the debugger can't tell me what is wrong, then maybe printf can. And I want to also print current used here, and then current next. Just let me know all these values here. Yeah, and here I want to not print a character, but an integer or something like that. Still crashing. We get one printf, and then current used already crashes. Now that's a bit odd. Of course, there's nothing in that file. The file is empty. So we can't put anything into that file. That's not very nice. Let's try ftruncate with 1 megabyte. Ftruncate, man ftruncate. Oh, it wants to have some includes again, so we copy in those includes. Great, and then ftruncate takes a file descriptor and a length. Okay. Ftruncate, file descriptor and length. Let's try. Maybe this works now. Oh yes, suddenly it works. Interesting. And also stores our data correctly. So you see that ftruncate is really important to call here. Otherwise you won't be able with mmap to write more into the file than the size of the file actually is. Okay. So we did that. And there's something in our game config. So let's try to look at that. Do we have a some Hex Editor? I think Visual Studio Code can do that. So let's take a look at this game config. Yeah, I want to open that in a Hex Editor. Ah, yes. And here we can see, interesting, we can see the pointer here. What's this? 80 and 07. 80 and 07. So maybe we should check what 1920 is in hex, and it would be 780. So this is actually our resolution here, 780. And then we have, we should have also the other one, right? I don't see the non-zero value here, but it should be somewhere here, because we passed 1080 there. Another thing that you might want to know and might need in A4 is attribute packed. With that, you can make sure that the struct is as small as possible. And now, again, the core dumped. Why did it dump? Core dump. Let's try again. Run it with GDB. Let's backtrace it. It crashed an add element in line 31. Again here. Now, I didn't change much. I just changed that it's now packed. Interesting. But the pointer seems to be valid. So maybe we want to print the pointers here. Let's run that. Is it really iterating through the list? Maybe not. Ah, yeah, it picks up a next pointer, but look at this address. This looks really different than the first one. Didn't we say they should be next to each other? How does that fit together? You might have noticed what we are doing. We are loading, we're opening a file, we are mapping this file into memory. Now it's already in memory. And this here, this next pointer, will be a pointer from the previous run of the program. So it's a virtual address. It's a pointer that is not valid. That doesn't make any sense anymore in our program right now. Oh. That's a problem, of course. So that means in the beginning, when we load this from the disk, we probably should make sure that everything is properly linked. So how do we do that? Well, we again take a pointer, struct config element pointer current is E. While current used is not 0, we want to make sure that current next is set to a useful value, because the previous value that we just loaded from the file doesn't make any sense to us anymore. So we can instead set it to this. And now it should work. Redefinition of current. Yeah, so you can just reuse the same variable here. A lot better, a lot better. I mean, we are now storing values, more and more values in there, as you can see. With every run, I'm storing more and more values because it's now stored on the disk. I want to try one thing, like, is this already shared memory? Can we already work with that? So let's try two different things here. So if we are PID 0, if PID equals 0, then we will, in both cases, we have to do this. This is the truncate, F truncate. Only one of them has to do that, actually. Only the writing end. And then if both of them overwrite the pointers here, that's also not really working. So maybe we can simplify that a bit. So maybe like this, current plus this. I think that's a bit safer. Because we don't want to store the pointer in there actually, because it won't be valid in another process. So storing a next pointer in there only makes sense if it's valid in all the contexts where it's used. So let's see, we have the current next here, but I mean, it's super easy to compute it, so why would we store it anyway? Okay. Struct config element has no member next. Yeah, I know that it doesn't have any member next anymore. But I thought I removed all of them, didn't I? Expected declaration or statement and enough input. This is wrong. This is something else. What is it missing? It's yes, I started this one here, but I need to close this one. So here, one of them adds element to the list, and the other one just prints them. Okay, this sounds good. Still, I get a core dump at the end, so that's still a bit weird. So let's debug this. It's important to debug all the errors that you get. Run, backtrace. This is in line 72. 72. Yeah, that's now a problem, of course, because I'm iterating here. I should check whether it's used. If it's not used, then we stop. Yes, a lot better. Okay. Okay. So let's see. We want to run this now in two programs. Let's open some terminals for that. So maybe like these two here. Now I will run this program. So let me first compile it. And now I will run it with mmap and I will truncate this config. Now if I run this, dot mmap files 1 with 0. I get a bus error. Okay, let's see. GDB run backtrace. It's crashing in line 54 while used is not 0. Yes, we need to truncate, of course, before that. Otherwise we cannot read if the file is new. GDB, let's just compile it again. We run this. Okay, so now it terminated normally. So we can run this and we get more and more values into our database. So let's truncate that again. So we have truncated that again. We can run this again. And now you can see that if I run this, now there should be 3 values in there. Now I truncate it, and here I will run this same thing, mmap files 1 with 1, and 1 will read. This one will only read, it will not write. You see, it's empty, it's not doing anything. Now if I start this program, it's already running now. It's stopping now at this location here in this get character line. That's where the program stopped, on the right side. Now I start on the left side my program to modify things in shared memory, but also in this file, and we let this one print it, and it got the value. So that's the first inter-process communication we have here. One process sent data to another process. And I think that's a good point for today to end. And tomorrow, no, not tomorrow, later, I think next week is the next lecture. Yeah, next week is the next lecture. And there we will continue with this example. So next week it's probably more coding and not much. I'm not sure I have any slides for next week. But the week after that, there will be slides again. So let's go through the questions in Menti. So we'll hide this one for a second. Is there a limit for how big an executable can get, or does it depend on the test or on the system resources? Can't test because of my low free disk space. Good question. Yeah, but it's something to try out. Maybe you can come up with a plan how you can still test this. Maybe there's some way to simulate a larger disk. And if you create a very sparse file, a sparse executable, then this might work. For this code, there are some parts in there that are very, very close to what you have to do in the exercises. So I would be more careful about providing this code. Just go ahead, try that on your own, implement that on your own, and then you have the same code. Without watching the lecture, of course, just sit down, implement the same things, go through the same ideas. I mean, we just try to use shared memory to let 2 processes communicate, implemented a linked list. You should be able to figure out how that works. Is there a lecture next week? As far as I know, there is. I can check, but oh no, next week is a big, is it a holiday? Maybe it's a holiday. I will schedule some lecture, so there will be some lecture. I might still have to send it out then. But we covered everything for A3, so I think as long as we're before the A4 deadline, I think the next lecture is still early enough. And you also had today all the basics that you need for A4. Okay. Yes, next week is a holiday. I also realized that, but we will figure out how it works. I'm curious how some people already know everything that is taught in this class and always finish the assignment so fast. Is there a Wahlfach where this is taught as well, or what? So that's the thing. Most of these things you can just learn on your own. I mean, what I'm showing you here in this course, and this is also the reason why I'm so often just in VS Code here and open the man pages, because all of this is documented. You just read the documentation, and I'm just showing you how would I approach these problems. I would open VS Code and check the man pages and read what's written in there. I didn't come up with anything that is not written in the man pages, right? Think about it. Everything that I told you is written in the man pages. You could have read them already, and so that's how some people are very fast. They just look it up in the man pages and are done. Malloc uses mmap for bigger allocation. What does mmap map to? Virtual address space to actual RAM addresses when initializing values. It's the same. So all types of memory allocation use virtual addresses, and they somehow map these virtual addresses to actual physical addresses. And some of the physical addresses go to RAM. Not all of them, but some of them. This is my first semester, and I already know that what they will teach me in ESP is wrong. Love it. Well, the thing is, there are reasons for that, right? Think about it. Timescan, if you think about the situation where you would tell a child that there's Santa Claus. Of course, it's a lie. There's no Santa Claus. Sorry if I ruined it for some of you now, but there isn't. And still, people tell their children there is Santa Claus and Santa Claus brings the presents, although they themselves know it's a lie. Why do they do that? Because it makes some things easier to explain, like why didn't I get the present that I wanted, or why is the present this year smaller than the present last year. It makes some things easier. And the same goes for the introductory programming courses. For most of you, learning how to write programs in C and C++ is already exhausting enough that these simplifications, these simple lies that make things easier to understand help you in the end. And later on, you can then figure out what actually is the case. Oh, I don't know, first semester. So it always depends. So for instance, I also took some third semester courses in my first semester. If you feel like you can do it, then why not? Sure. How do I check the binary size of a program? How it changes while running? I'm not sure whether the binary size changes while running the program. I'm not sure I understand the question correctly, but I mean, I just showed you how to check the size of a file. So what I do is I type in LA, which is a shortcut for ls minus LA. And then you can just type in the binary file and you see the size of the file. And if I compile that again, so let's compile this with GCC here, and then you can see here it's still the same file, and then I maybe remove the -G flag and you will see that the file size changed. So this is how you see the file size. Just look at the, I mean, you can use any file manager to check that as well. Do you have your own shortcuts for VS Code? I'm most of the time writing papers today, so or project specific project specific texts like project proposals, stuff like that. So it's more written text, less code. And I have a lot of shortcuts for writing text, but not for writing code. What's the difference between creating shared memory with Shm Open mmap and Shm get Shm at? Those are different POSIX calls that you can use, and Shm Open and mmap, or Shm Open would be named shared memory, Shm get, Shm at would be unnamed shared memory, as far as I remember. But I would have to look up in the man pages what exactly the differences are, because I rarely use Shm get man, Shm get. It says, yeah, allocates some shared memory, and I think it uses a key. I think maybe it was some number or something, but I would have to look up what exactly they work like. Okay, let's just make some room here. So different ways to get shared memory. How many lectures will there be? I think in total maybe about 7 or 8, something like that. So maybe two more, 3 more, something like that. What is portable code? Portable code, if so let's say you're using Arch Linux and I'm using Ubuntu, and if your code doesn't work on my system but on yours, then it's not portable. Let's say you're using Windows and I'm using Ubuntu, and my code works on both of these systems, then I would say that's rather portable code. And that's actually possible. You can write C programs that you can compile on a native Windows just the same as on a native Linux. That's portable. So, you know, as we learn how to ignore hints from the user programmers, exactly, actually, yes. You actually implement everything you got to know here. You will implement mmap from scratch, from 0. It doesn't exist, so you implement it from 0. munmap, Shm Open, Shm close, like unlink. You will implement maybe parts of open and close, read, write. You will implement fork from scratch, pthread create, pthread join, pthread cancel, pthread exit, all from scratch. Exec from scratch. So you start with empty files, basically, no to-dos, nothing. You have all the freedom in the world and implement those system calls. What exactly do you teach? What is SSD and what else? I teach operating systems, system level programming, secure software development, InfoSec, side channel security. Not sure, maybe I missed something, but yeah, of course, introduction to scientific working, and then of course I supervise some bachelor theses, master theses, typical stuff. Is it now also relevant for A5? This part, well, the linked lists, definitely, yes. Okay, so you can't look up man pages if you don't know these commands exist or how they are named. Yes, but then, I mean, you know what you want to do, so you can always Google POSIX and then describe what you want to do, and I'm pretty sure that you would find the right command for that. If you say POSIX allocate shared memory, I can try what I find, but I'm pretty sure that I will try that now. I'm typing now POSIX shared allocate shared memory, and the first thing that I find is a man page Shm overview. So the first thing it points me to is this man page here, Shm overview. Ah, very nice. An overview of all the functions I might need. So then you have starting points. And that was the first result on Google that told me I should look up this man page. Okay. Could you show us how to check the current user RAM from a program using htop? Sure. Maybe let's do this one again, and I will hide the Menti for a second so that we can see this. So I will open this second window here. Okay, you can see here up here, this is the RAM of my system, right? I have like 64 gigabytes, like 62.7 gigabytes. I don't know where the rest has gone. Let me just open one more. Okay, so if you think about it, I mean, there's like 6.7 gigabytes in use right now. And now if I run our simple mmap example, the mmap1 example from earlier, you can see that it barely changes anything. But I will show you one more thing. If I let me just hide this window again, and I will open mmap1 again. And now what I will do is, if it's valid, I will actually say, well, for size ti or j equals 0, j smaller than okay, this is a gigabyte of allocation, so smaller than a gigabyte, and then I will say j, that's a what kind of point t at offset j, right? Just some, I don't care which value. Let's write j mod like times 37. Sure, times 37 is always great. It's a prime number. Let's compile this. So we call GCC with our mmap1 example. And now you can see that the memory allocation is really increasing here. I can filter here even. Oh, now it crashed. Let's try that again. So I'm starting it one more time, and you will be able to see how the memory usage increases. So this is really memory usage, because I was right. And as it goes, it even gets my system out of memory when I run this, as you have realized. So the system gets, like, it starts stuttering. So let's maybe remove this one again. So if I don't write into this array, if I don't initialize all this array, then I can run this, and you will be able to see that the memory consumption stays pretty low. You can here see virtual grows, but reserved, shared, that stays at the same. Overall, the system memory usage also stays pretty much the same. Yeah. So virtual is now at 128 terabytes. So that's basically it. So let's continue with the questions. So we did this, yes. So mmap is enough to create shared memory. Yes, you only need to know one syscall. It's mmap, well, and Shm Open if you want to have named shared memory. If I use mmap with map anonymous and map shared, what does the shared flag do here? Can I somehow communicate with another process here, even though it is not backed by a file? If so, how? Yes, the thing is, so that's a very good point. The thing is, someone would have to be able to work with the same file descriptor. So how is that possible? Men fork. Okay, let's see. What does fork say about that? Child process is an the child process is an exact duplicate of the parent process except for the following points. PID, parent PID, memory logs, process resource utilizations, signals, semaphores, logs. Does it say anything about file stuff? Here. The child inherits copies of the parent's set of open file descriptors. I think it's possible. I think it's possible to share an anonymous mapping. All variables, all objects, local, global, shared malloc variables, all allocated on virtual memory. Yes, it is not possible to directly work on physical addresses, even for the operating system, but we learned that next semester. It's not possible to directly work on physical memory. If you enable virtual memory, that's one switch in the CPU, then the CPU works on virtual memory all the time, never on physical memory. Okay, that's it. Those were all the questions. Thank you, and see you in the next lecture. Bye.